welcome to G-Fun Facts Online. Today we're talking about one of the most powerful technologies ever created, artificial intelligence. It's reshaping our world, but it has a massive, hidden cost. AI is a double-edged sword. On one side, it's a voracious consumer of energy, potentially worsening our climate crisis. On the other, it's a powerful tool that could unlock unprecedented efficiencies and help us build a sustainable future. This is the energy dilemma of AI. So let's dive into the immense environmental cost of the AI revolution and then explore the groundbreaking ways it's being harnessed to save our planet. Let's start with the dark side, AI's insatiable appetite for power. The magic of modern AI, especially the large language models or LLMs like ChatGPT, doesn't come from thin air. It's forged in massive, energy-guzzling data centers. The environmental cost breaks down into three main areas: the electricity it consumes, the water it drinks, and the waste its hardware creates. Let's talk about that electricity first. Training a large AI model is an astonishingly energy-intensive process. Imagine feeding a machine the entire internet and asking it to learn grammar and concepts. This requires trillions of calculations. To put this in perspective, researchers estimated that training OpenAI's GPT-3 model consumed about 287 megawatt-hours of electricity. That's enough to power 120 US homes for an entire year. The carbon emissions from that single training run were about 552 metric tons of CO2, equivalent to what 120 gasoline-powered cars produce in a year. And the problem is getting worse. Fast. While companies are secretive about the exact numbers, estimates suggest that training GPT-4, the next version, used as much as 50 times more electricity. A peer-reviewed study put GPT-4's carbon emissions at over 7,000 metric tons of CO2, and it keeps climbing. Meta's Llama 3.1 model, released in 2024, is estimated to have produced nearly 9,000 tons of carbon emissions just during its training. And that's just the training phase, the inference stage. When you or I actually use the AI to ask a question or generate an image, also uses a lot of power. A single chat with an AI like ChatGPT is estimated to use about the same amount of energy as fully charging your smartphone. That might not sound like much, but scale it to billions of interactions every day, and the numbers become staggering. One estimate suggests that if Google integrated this kind of AI into all of its 9 billion daily searches, the energy required could be up to 30 times greater than what it uses now. Where does all this power come from? Data centers. These are the physical backbone of the digital world, housing tens of thousands of power-hungry servers. Globally, data centers already accounted for about 1.5% of all electricity consumption in 2024. But with the rapid adoption of AI, the International Energy Agency projects that this figure could more than double by 2030, reaching a level of demand slightly higher than Japan's entire country consumes today. Some forecasts are even more alarming, suggesting data centers could use as much as 8% of all global electricity by 2030. This growth is putting a huge strain on electrical grids. In some parts of the US, utility companies have reportedly had to restart retired coal plants just to meet the surging demand from new data centers coming online. Beyond electricity, AI has a second, hidden thirst: water. Data centers generate a colossal amount of heat, and they need to be kept cool. Many use a process called evaporative cooling, which consumes millions of gallons of fresh water. The scale is mind-boggling. In 2022, Microsoft's global water consumption jumped by 34% in a single year, reaching nearly 1.7 billion gallons, a surge driven largely by its AI development. In 2021, Google's US data centers alone consumed over 3 billion gallons of fresh water for cooling. This water footprint extends down to the individual models. Researchers estimate that training a model like GPT-3 can use around 700,000 liters of clean fresh water. Even just talking to an AI has a water cost. A simple conversation of 20 to 50 questions with ChatGPT is estimated to consume about half a liter of water. Projections show that by 2027, global AI demand could require up to 6.6 billion cubic meters of water annually. That's more than the total annual water withdrawal of entire countries like Denmark. This is a huge problem, especially since many data centers are located in water-scarce regions, creating direct competition for a vital resource with local communities and farmers. Finally, there's the hardware. The environmental impact of AI extends through the entire life cycle of the specialized chips that power it, from the mine to the landfill. AI runs on powerful processors like GPUs. Manufacturing these chips relies on mining dozens of rare earth metals and critical minerals like lithium and cobalt. This mining is often environmentally destructive, causing deforestation, soil erosion, and water pollution. For every ton of rare earth elements produced, the mining process can create thousands of tons of toxic, sometimes radioactive, waste. The rapid pace of AI development creates another huge problem: electronic waste, or e-waste. The AI arms race pushes companies to replace their hardware at a frantic pace, sometimes every 12 to 18 months, compared to a typical 3 to 5 year cycle for other IT equipment. This accelerated obsolescence is predicted to cause a surge in e-waste. A 2024 study warned that the AI boom could add between 1.2 and 5 million metric tons of e-waste every single year by 2030. This waste is hazardous, containing toxic substances like lead and mercury that can leach into soil and groundwater. Globally, only about 22% of e-waste is properly recycled. The rest ends up in landfills or is shipped to developing countries, where it's often dismantled under unsafe conditions. Now, it would be a mistake to only focus on these negative impacts. The same incredible computational power that makes AI so energy-hungry also makes it a revolutionary tool for optimization and efficiency. Let's flip the sword over and look at how AI is being used as a catalyst for a more sustainable energy future. The first area is the power grid itself. Modern electricity grids are incredibly complex, especially with the addition of intermittent renewables like wind and solar. AI is becoming essential for managing this complexity. For example, one of the biggest challenges with renewables is their variability. The sun doesn't always shine, and the wind doesn't always blow. AI algorithms can analyze huge datasets, weather patterns, satellite images, sensor data, to predict renewable energy production with incredible accuracy. This allows grid operators to plan for fluctuations, reducing the need for fossil fuel backup plants. In one case, Google's DeepMind developed an AI that could predict wind power output 36 hours in advance, which led to a 20% increase in the value of that wind energy. AI also makes the grid more stable. By monitoring the grid in real time, AI systems can detect anomalies and predict equipment failures before they happen. This is called predictive maintenance. It can identify an aging transformer or a strained power line, allowing for repairs to be made proactively. This not only prevents power outages, but also extends the life of critical infrastructure, saving money and resources. Studies show AI-driven predictive maintenance can cut downtime by up to 30%. Next up are buildings and cities. Buildings are responsible for a huge chunk of global energy use, mostly for heating, ventilation, and air conditioning, or HVAC. AI is making these systems dramatically smarter. An AI-powered building management system can analyze dozens of variables in real time: outdoor weather, indoor occupancy, sun angles, humidity, to continuously optimize the HVAC system. Instead of running on a fixed schedule, the system can proactively adjust heating and cooling to ensure comfort while eliminating wasted energy. The results are impressive. An AI solution implemented across over 600 school buildings in Stockholm led to a 15% reduction in electricity use. In New York City, a 32-story office building installed an AI system and saw its HVAC energy consumption drop by nearly 16%, saving over $42,000 in just 11 months. And famously, Google used its own DeepMind AI to optimize the cooling of its data centers, which resulted in a 40% reduction in the energy used for cooling. AI is also cleaning up the transportation sector, a major source of greenhouse gas emissions. AI-powered logistics platforms can analyze millions of variables like real-time traffic, weather, and delivery windows to calculate the most fuel-efficient routes for delivery fleets. Companies like Walmart and DHL are using these systems to cut fuel consumption and emissions. Studies have shown this kind of route optimization can reduce fuel use by 20 to 30%. One major logistics company reported saving $50 million in fuel costs and avoiding 100,000 metric tons of CO2 emissions annually after implementing an AI system. Finally, AI is streamlining heavy industry. Manufacturing processes are often highly energy-intensive. I can analyze complex operations to find inefficiencies. For instance, a semiconductor manufacturer used an AI solution that resulted in $1 million in energy savings and a reduction of 10,000 tons of carbon emissions annually per plant. A food and beverage company reported a 20% reduction in energy consumption after deploying an AI-powered energy management system. Beyond the factory floor, AI is optimizing entire supply chains. By more accurately forecasting demand, AI helps companies avoid overproduction, which cuts down on the energy spent making, transporting, and storing excess products. So we have this profound dilemma. AI's potential to drive both unprecedented energy consumption and revolutionary efficiency gains means its ultimate environmental impact is not yet decided. Navigating this requires a multi-pronged approach. One of the biggest challenges we face is something called the rebound effect, or Jevons paradox. This is the idea that as technology makes using a resource more efficient and cheaper, our overall consumption of that resource might actually increase because the lower cost encourages us to use it more. For example, if AI makes data processing cheaper, it might just spur an explosion of even more complex applications, leading to a net increase in data center energy use. One study found that for every 10% improvement in AI computing efficiency, there's historically been a 20 to 30% increase in its overall use. We have to plan for this rebound effect to ensure AI's efficiency gains lead to real, absolute reductions in energy consumption. To counter the negative side, a new field called Green AI is focused on making AI itself more sustainable. This involves both software and hardware innovations. On the software side, researchers are developing techniques to make AI models smaller and more energy efficient. This includes methods like pruning, which removes unnecessary connections in a neural network, and quantization, which reduces the model's numerical precision to lower its computational needs. Another technique is knowledge distillation, where a small, efficient student model is trained to mimic a large, complex teacher model. On the hardware side, the future lies in rethinking the physical architecture of computation. One exciting area is neuromorphic computing, which involves designing chips that mimic the structure of the human brain, which is incredibly energy efficient. Another is optical computing, which aims to perform calculations using light instead of electricity, potentially using a fraction of the power. But technology alone won't solve this. We need a robust framework of policies and industry standards. Governments are starting to act. The European Union's AI Act, for example, requires providers of large AI systems to report on their energy consumption. In the US, a bill has been proposed to study AI's footprint and develop reporting standards. Key policy actions should include mandating transparency, forcing tech companies to report standardized data on their energy, water, and carbon footprints. We also need to incentivize green practices, like giving tax credits for data centers powered by renewable energy. And we must strengthen regulations around e-waste to promote a circular economy for AI hardware. In conclusion, artificial intelligence stands at a critical juncture. It's a true double-edged sword in the fight against climate change. One edge threatens a future of spiraling energy demand and resource depletion. The hidden costs are real and growing. The other edge offers a brighter path, providing the intelligence to orchestrate a clean energy transition and eliminate waste from our oldest industries. The direction we take is not preordained, it's a choice, and it comes with a profound responsibility. The future of AI's energy impact depends on the decisions we make today, from the researchers developing efficient algorithms, to the tech companies prioritizing sustainability, to the policymakers creating smart rules of the road. The energy dilemma of AI isn't just a technical problem, it's a societal one. By fostering a culture of green AI and demanding accountability, we can wield this double-edged sword not as a weapon of environmental self-destruction, but as a crucial instrument in forging a sustainable and energy-efficient future for all of us. Thanks for listening to G Fun Facts Online.